This is B. Naresh, working as assistant professor in IC department. And today's topic is analysis of common source JFET amplifier. So in the last two sessions, we discussed that the FET construction as well as the characteristics in JFET configuration as well as the MOSFET configuration. The major application of the FET is acts as a amplifier. So for this amplifier, so we also discussed that how we can maintain the proper operating point by the applying of the biasing voltages between the gate and the source as well as the drain and the source. And based on the FET configuration, we have the three types of the terminals in a FET. One is represented as a source, another one is represented as a drain, then another one is gate. So we can configure the three types of the configurations, like one is represented as a common source. It is represented as the CS, as well as the common drain. It is represented as the CD, as well as common gate, so C. So we can configure these three different types of the configurations: common source, common drain, and common gate. So in this case, if we consider the common source configuration, means that the source terminal is common for input side as well as the output side. So if the source is a common out of the remaining two terminals, so one is acts as the input, another one is acts as the output. Hence, in this common source, the gate terminal is acts as the input and the drain is acts as the output terminal. And the source is a common with this gate as well as the drain. Similarly, in a common drain, so drain is a common, means gate is acts as input terminal, source is the output terminal. So common gate, in a common gate terminal, gate is a common terminal and source is the input side, drain is the output side. So in this session, we are going to observe the common source JFET amplifier by using the small signal model. And from this, from the characteristics, and we observed that the two types of the characteristics. One is drain characteristics, or it is also called as output characteristics, and another one is a transfer characteristics. From these two characteristics, we observe that the drain current is a functioning of the applied biasing voltage between gate and the source as well as the drain and the source. So hence, based on these parameters, now we are going to observe how we can design the JFET is acts as amplifier under this common source by using the small signal model. So based on the small signal model, we can represent this ID is represented as GM times of VGS plus 1 by RD into VDS. So where GM is nothing but a transconductance and the VGS means the biasing voltage between gate and the source, means the potential difference between gate and the source, where the small RD is nothing but a internal drain resistance and the VDS is again the potential difference between drain and the source. So let us consider a common source JFET amplifier, means here I consider the JFET and we know that the three terminals, one is the drain, source, another one is a gate. Here the gate is acts as the input side, hence it is represented as input side. A biasing resistance is a biased with a drain, that is represented as a capital RD, and it is biased with a voltage is VDD. So for this case, the first time the source is common for input side and output side, hence the output is measured across the output side. So now by using this configuration, we are going to redrawn into a small signal model. So here the small signal model is represented as, so let us, if you recall this ID function, the drain current from the characteristics and the small signal model. So ID is represented as GM times of VGS plus 1 by RD into VDS. Hence, here it is represented as, so this is the drain output side. The drain current is represented as GM into VGS plus 1 by RD into VDS. And generally in a JFET, gate is open, hence the gate terminal is open. And across the gate, it allows the gate current that is represented as IG. And for input side, so here the gate side, we apply the input voltage, hence here I taken as the VI. Then, and output side, we need to allow this drain current. And from this mathematical representation, so ID is represented as GM into VGS plus 1 by RD into VDS. Hence, I represented as, we have the two types of the currents. So one is represented as GM times of VGS. Another one is represented as 1 by RD into VDS. Hence, so this ID, the drain current, is a flows across the drain terminal. Output side, I use this drain, and here it is represented as V0. So from this representation, so this is small RD is the internal resistance, and a capital RD means this is the external RD is biased with biased across the drain terminal, that is capital RD. And the source is the common, where S is the source. Source is the common for input side and as well as the output side. And drain is taken as the output side. Gate is taken as the input side. Now by using the small signal analysis, now we are going to observe the parameters like a gain and input impedance and output impedance. So here the FET contains the voltage gain first. So hence we are going to observe the voltage gain. Then we need to observe input impedance as well as the output impedance. So from the circuit, if you observe the circuit, so what is the circuit? So we have this one. So this is gate, and here it is represented as VGS, and here we applied a VI. Then let us take this is the drain current flows. One current parameter is represented as GM into VGS plus this is internal drain resistance small rd times of, and this potential is represented as the VDS, and externally we place the a load resistance, or it is also called as the drain resistance, and then we need to measure a output voltage across the capital RD, and this is connected to ground, means this is the source terminal, this is the gate, and this is the drain terminal. So if you observe from this circuit, if you want to represent, so what we observe from this case, the VI is represented as, so here the VI is represented as VGS. So hence parallelly the voltage is the same. Hence from this representation, here I taken as the input voltage is equal to the potential difference between gate and a source, that is represented as VGS. And similarly, we know that again from this circuit, the output voltage V0 is again proportional to the potential difference between drain and the source. Hence, I consider as V0 is equal to VDS. And again, from the small signal model, we know that the drain current is represented as GM times of VGS plus 1 by RD times of VDS. So this is taken from the small signal model analysis. And from this, or otherwise from this, you can represent this ID is equal to GM VGS plus 1 by RD into, means V by R or VDS by RD. Now, and from this case, again from the small signal equivalent circuit, if you want to call this output voltage, so what is the V0? V0 is equal to, so means drain current is the flows like this. Let us assume that if it is a load resistance, hence the load current is also flows. So the load current flows through this RD, and we know that whatever the drain current is delivered, that should be passing through the load resistance. Hence that current I consider the IL. But from this circuit, if you observe the current flow direction, so the drain current flows like this, and the load across the load the current flows like this. Hence the current flow direction is opposite. Hence I consider as V0 is equal to So if you want to write the voltage drop across this capital RD resistance or external load resistance, it is represented as V naught is equal to. So which current we assume across this RD? Here we assume that the load current IL, hence it is represented as IL times of RD. But from this circuit analysis, whatever the drain current is delivered, the same amount of the drain current is flows through the external load resistance, that is RD, that is the reason. But the current flowing direction is opposite, hence, and this IL here I represented as that is equal to minus ID. The same current is the flows. Hence, the IL is replaced by, so with a minus ID, hence V naught is represented as minus ID times the capital RD. Now from this, now we need to find out. So from this, so this is already we observed V naught is equal to minus ID into RD. Now we know that ID is equal to GM into VGS plus 1 by RD into VDS. Hence, I am going to substitute this ID parameter. So, I substituted the ID value is GM into VGS plus 1 by RD into VDS, and this is multiplied with capital RD. And then simplify this evolution. So, hence what happens? So, now I am going to multiply this one. V naught is equal to minus GM VGS into capital RD plus 1 by RD, small rd, this is into VDS into capital RD. The same expression I represented as, so minus, this is minus is a multiply. So hence minus GM into VGS capital RD minus capital RD by small rd into VDS. Now, and previously what we observed, so here we observed that, so VI is from this circuit analysis, we observe that Vi is equal to VGS and V naught is represented as VDS. Means VGS is equal to Vi and VDS is represented as V naught. So hence here I am going to substitute this VGS. So means Vi is equal to VGS. At VDS, we know that V naught is equal to VDS from the circuit analysis. Hence, I am going to replace these two terms with VI and V naught values. Why I am going to replace with in terms of VI and V naught means if you want to determine the gain, the gain is defined as it is a ratio of output parameter to the input parameter. So in this case, we are going to define the voltage gain. Hence, if you want to define this voltage gain, it is defined as it is a ratio of output voltage to the input voltage, means V naught by VI parameter. That is the reason. So here I converted in terms of V naught and VI terms, means VGS is replaced with VI and VDS is replaced with V naught. Then we can take this outside. So means we have the two V naught terms. Hence V naught is this. If I reckon this is the outside, so it becomes plus V naught plus capital RD by small rd into V naught, that is equal to minus GMVI into capital RD. And from this, so now from this what we observed here, so V naught plus capital RD by small rd into V naught. So means from these two terms, the V naught is a common. Hence, if I take in the V naught is a common, that becomes 1 plus capital RD by small rd, that is equal to minus GM into VI into RD. Just take the LCM. So in this case, what happens if we are taking the LCM, that is small rd, means small rd plus capital RD, that is equal to minus GM VI into RD. So from this, I am going to find out only the V naught term, the output voltage. So hence you take this term is taken to outside. Now it becomes small rd by capital RD plus small rd. So hence, so you can multiply this one, V naught is equal to minus GM VI capital RD into small rd by small rd plus capital RD. And again, so from the JFET or from the FET analysis, we have the one relation. So we know that one relation between the amplification. So mu is equal to GM into RD. So we have this relation from the FET characteristics. So the amplification factor, where mu is the amplification factor, Gm is the transconductance, and the small r is the internal drain resistance. So hence, and from this term, this is Gm and this is Rd, small rd. This product is replaced with the mu factor, hence it is represented as, so now hence V is equal to Gm and the small r is replaced with the mu, and Vi times of capital Rd by small rd plus capital Rd. So that is the reason it is represented as V0 is equal to minus mu Vi into capital Rd by small rd plus Rd. Now if you want to determine the voltage gain for this common source JFET amplifier, so now I'm going to define what is the voltage gain. So here the voltage gain is defined as it is a ratio of output voltage to the input voltage. So just now we got that the output voltage V0 is equal to minus, so mu times of Vi into capital Rd by small rd plus capital Rd. Hence, I'm going to find out this voltage gain AV is equal to V0 by Vi. Hence, minus mu times of Vi into capital Rd by small rd plus capital Rd by this Vi. So this Vi is a get cancelled. Hence, the AV becomes minus mu times of capital Rd by small rd plus capital Rd. Hence, this is the voltage gain of common source JFET amplifier, where the mu is amplification factor and it is also represented as mu is equal to Gm into small rd, and where the capital Rd is called as the load resistance or drain resistance, external drain resistance, and the small rd is internal drain resistance. It is also called as AC resistance, internal AC resistance. So this is the voltage gain for a common source JFET amplifier. Now we are going to calculate the input resistance. Means, according to the generalized formula, we know that the R means it is the ratio of voltage to the current. And now we are going to observe this input resistance at the input side, hence Ri, or it is also called as Zi, is represented as it is a ratio of input voltage to the input current, that is Vi by Ii. Now from the circuit, if you recall the circuit, so from the circuit we know that the Vi is equal to Vgs and the input current. So from this small signal model, the input terminal here it is acts as the gate terminal, hence the input current is represented as Ig. So hence Vi is equal to Vgs and Ia is represented as Ig. So hence that is the reason we defined as, we assume that Vi equal to Vgs and Ia is equal to Ig. Hence in the place of Vi, I replaced it with Vgs, and in the place of Ii, I replaced it with Ig. And again, from the characteristics and from the construction of the JFET, we assume that the gate current is very, very small. Hence, I'm going to assume the gate current Ig is 0. If Ig is 0, the input impedance or input resistance, that becomes infinite. So generally, while satisfying the amplifier condition, means from this analysis we need to offer a very large input impedance to drive the drain current in a JFET amplifier. Now similarly, we need to calculate the output resistance. So means, again the output resistance means R0, it is a ratio of voltage to the current, and those two parameters we need to consider at the output side. Hence it is represented as, it is a ratio of output voltage to the output current when the input voltage is constant. So that is the reason it is defined as, the R0 is defined as, it is a ratio of output voltage, that is represented as the V0 to the the output current, that is I naught. So from the circuit again, so if you recall the circuit output side, if I taken the output side, so what is the output side? It is contained the drain side, and the parameter is represented as Gm into VGS plus, and this is small rd, and externally we connected as a capital RD or a load resistance, and here it is represented as the potential difference between drain and the source. Now we are going to find out the output voltage across the load resistance. So from this circuit analysis, from this common source configuration, we consider as the output terminal is across the drain side, hence the I naught is replaced with drain current ID, and from this representation the V naught is directly proportional to this VDS, hence V naught is represented as VDS when the input voltage is 0. So from this, if I'm writing, so where we know that, so from the small signal model, we know that the ID is represented as Gm into VGS plus 1 by RD into VDS. So hence, I use this a small signal analysis drain current. ID is represented as Gm into VGS plus 1 by RD into VDS. And to determine this output resistance, we calculated this output impedance when the input voltage is 0. So means whenever consider the input side, this is Vi is a 0, means, so we know that this is VGS, and from the circuit we know that Vi is equal to VGS. Hence, what happens if Vi is equal to 0 means VGS is also becomes 0. So we maintain this input voltage is 0 or the input voltage is constant. Hence, from this small signal model, we taken as the Vi is exactly equal to means VGS. Hence, we consider as the input voltage is 0. Hence, VGS is also represented as it. So in this term, I am going to substitute is a 0, means 0 is multiplying the 0. Hence, the ID becomes only 1 by RD by VDS. Now, we can substitute these two parameters and the VDS, V0 parameter and ID parameter to determine this output impedance. R0 is represented as VDS, means VDS. ID is replaced by VDS by RD. So hence this VDS, so that VDS and VDS is get cancelled, then it becomes smaller. So hence R0 is equal to small RD. So in this case, here I am not considering the external load resistance or external drain resistance. So if you are not consider the external load resistance, the output impedance is exactly equal to the internal drain resistance, that is our internal AC resistance. Suppose if you are considering the external load resistance, if you want to calculate the total output impedance along with external load impedance or external drain resistance. Now, so I use the simplified circuit. So this is the internal drain resistance or AC resistance, and the capital RD is the external drain resistance, or it is also called as load resistance. So for this case, now I'm going to calculate the total output impedance. It is represented as Z0 dash. And from this network, we can observe that these are the two resistances are under the parallel configurations. Hence, the total output impedance Z0 dash is represented as that internal drain resistance is parallel with the external drain resistance, that is capital RD. So hence, so that is the reason Z0 dash is represented as RD is parallel with the capital. So means again, so this Z0 dash becomes small rd into capital RD by small RD plus capital RD. Then if we want to drive the drain current, means we need to behave the FET is acts as the amplifier, means the maximum whatever the flow is generates, that should be flowing through the load. So here the load resistor, the load is replaced with the load resistor, and here we consider as that external resistance or a load resistance is the capital RD. So if you want to allow the maximum current through this resistance, means we need to allow whatever the current is generates across the drain, that should be flowing through the load to satisfy this amplifier principle. Hence, we need to take as some assumption. We have the two resistances here. One is the internal AC resistance or drain resistance. One is the external load resistance. To allow the maximum current towards the external load resistance, the condition should be that internal drain resistance must be much greater than of external load resistance or external drain resistance, that is capital R. And we know that under the parallel configuration, if the two resistances are unequal, and that parallel combination is gives the small equal to smaller resistance. So means if RD and this is RD is not equal to capital RD, if small rd is not equal to capital RD. If suppose if small rd is equal to capital RD, the parallel combination is always half of the given resistance. Then if the two resistances are unequal, the parallel combination is gives equal to the smaller resistance value. Hence here we taken as capital RD is a very small compared with your internal AC resistance, hence the Z0 dash is represented as capital RD. Under this condition means it indicates that whatever the current is generates across the drain, that maximum current is flowing through only the load. So that is nothing but your capital RD. So this is up to this point. We observed that the analysis of common source, the JFET amplifier. Then in that we identified the voltage gain and the input impedance and the output impedance. Now we are going to observe what happens when the source resistance is added with this JFET amplifier. For this case, let us consider. So in the previous case, I am not considered the source resistance, means directly the source is connected to ground potential. So in this case, now I am going to connect the source resistance to this source terminal. Again, we are going to choose the common source JFET amplifier, but only the modification is here I am going to place the source resistance for this common source JFET amplifier. Means gate is the input side, again drain is the output side. A load resistance or a drain resistance is biased with a drain with the biasing voltage is V plus, or it is also taken as the VDD. And a source resistance is biased across the source terminal. Then now we need to analyze how the source resistance affects the gain parameter or input impedance or a output impedance. To analyze this the voltage gain or input impedance or output impedance, first we need to redraw into a small signal model for this common source amplifier with source resistance. Hence, so this should be replaced with so here I considered. So we know that the JFET, this is JFET, and for this case the small signal model is this is the gate side, and output side it contains drain, and the common terminal is the source. It contains based on the ID relation, and we know that ID is equal to Gm into VGS plus 1 by RD into VDS. Hence this is the one current source, Gm into VGS plus, and this is small RD, and across these two potential we are going to observe the VDS. So hence up to this point, so gate side, and this is the drain output side. So this is the drain output side, and internal resistance, this is small RT, means ID is equal to Gm into VGS plus 1 by RD into VDS, means this is a potential difference VDS internally. And now if you observe the circuit, a RD is a place, so and this is external RD, and this is a source resistance RS is biased with the source terminal, that is RN. And your input is biasing through gate and a source, means with respect to lower potential. Hence this VI is connected between the gate terminal and this lower potential. This lower potential is ground potential, and V0 is also measured from the drain to the lower potential. Hence the V0 is measured from the lower potential drain to the lower potential. Now, by using this circuit, now we are going to analyze the voltage gain as well as input impedance and output impedance. Now, we need to see how the source resistance, while adding the source resistance, how it should be affected on these parameters to analyze the amplifier analysis. So, let us consider the same circuit. So, now I'm going to analyze. So, from this circuit, so we know that, so actually, we know this ID is represented as Gm into VGS plus 1 by RD into VDS. Now, this total product is I taken as I1 current. And this 1 by RD times of VDS I taken as I2. Hence, I represented this ID is equal to the summation of I1 and I2. So, from this analysis, and we observe that I1 is represented as Gm into VGS. Hence, I taken as I1 into Gm into VGS. Suppose if you want to identify this I2 from this current, so means how to write this I2 is equal to ID minus your I1. Now, what is ID value? So, ID is anything but, so this is ID minus I1. I1 is taken as your Gm into VGS. Hence, so for this, I am going to substitute this I2 value is ID minus Gm into VGS. Now, what is ID value? Again, you can substitute. ID is equal to Gm into VGS plus 1 by RD into VDS. Then, again from the circuit, so this is the I2 value. Whenever we required I2, they can use this one, ID minus Gm into VGS. And again, from this, an external drain resistance, let us consider this is the load. So hence, the load current is flowing through this external load resistance that is represented as capital RD. Now I'm going to observe how much voltage drop is allows across this load resistance that is represented as V0 is equal to I into R. Means I consider as the load current, and R means I consider the load resistance that is observed as RD. But we know that whatever the drain current is generates, the same amount of the current is flowing through the load with the opposite direction. Hence, I'm going to take this IL is equal to minus ID. Hence, the V0 is represented as this IL is replaced with minus ID. Hence, V0 is represented as minus ID times of capital RT. Now I'm going to substitute all these parameters. And let us consider for the input side. So in the previous case, if you are not consider the source resistance means, and we taken as RS is a 0 means that is a short circuited, then means it takes as VA is directly VGS. But now we need to calculate the input voltage from this gate terminal to this lower potential. So if you want to write this one, so up to the source terminal without, if you are considering this RS, we know that VA is equal to VGS. Now, along with the voltage drop across the source resistance that is represented as Vs. So hence Vs is equal to some current is the flows, and along with this RS, that is through this RS resistance. Hence that voltage drop across the source resistance I consider as a Vs. Hence, so from this circuit, it is a combination with means the VGS voltage source as well as the Vs voltage source. Hence, for this input loop, we represented as the input voltage VA is represented as VGS plus Vs. Now, what is the Vs? Actually, so here, so which type of current flows? If you observe the JFET amplifier construction, and this is the JFET, and external load resistance is biased with a VDD, let us take, and the source is biased with a source resistance is RS, and let us take this is the input. So here a drain current is the flows, and in generally we know that IS is represented as the summation of gate current as well as the drain current, or from the construction and the characteristics, the drain current is a flows from the drain to the source means. So, and again from the JFET analysis, the gate current is a very small. Hence, if I assume this IG is equal to 0, the source current is approximately equal to the drain current. Hence, across the source resistance, the same drain current is a flows. Hence, the Vs is represented as I into R. Means which current is the flows here? The drain current is the flows. Hence, I consider as ID along with the source resistance is Rs. So from this, now I'm going to find out the VGS parameter. So from this relation, just you retrieve this VGS parameter. The VGS is equal to Vi minus this term I taken to outside. So that is Vi minus ID into Rs. Now, similarly, if you apply the KVL at output loop, so what is the KVL at output loop? So means, so let us take this is, and here which current is the flows? This is Rs. So this is the output side. So I'm going to take this one. So hence this is ID into RD plus, and this is again the voltage drop across this. So this one, the voltage drop across this internal resistance is under this network. So here I assume that some drain current is the flows. Hence the voltage drop across this external resistance, that is represented as ID into RD. And similarly, the voltage drop across this internal resistance is VRD. And similarly, the voltage drop across this Rs I represented as a Vs. And here this is the voltage drop across VRD is a VR. Now we know that, so under this internal resistance, it allows the I2 current. Hence, this VRD I represented as I2 into small rd. Hence, this VRD is replaced with I2 into rd. And just now we observed that the Vs, the voltage drop across the source resistance is ID times of Rs, that is equal to 0. Now initially we observed that ID is represented as I1 plus I2. So we know that I2 is equal to ID minus I1. So what we observed from that, I2 is equal to ID minus I1 is nothing but your GM into VGS. Hence, now I'm going to substitute this value, the I2 value, ID minus GM into VGS here. So hence, this one I'm going to substitute in the place of I2. So what is I2 value we got? ID minus GM into VGS along with a small RD plus ID into RS. Now you can simplify here. Then after this simplification, so so that is equal to IDRD plus ID into small rd minus GM into VGS into small rd plus ID into RS, that is equal to 0. Again, we know that one more relation, and the relation between the three characteristic parameters like amplification factor and the transconductance and internal drain resistance. That is, we know that mu is equal to GM times of small rd. So if you observe this relation here, that this is GM and a small rd, hence I replace it with a amplification factor. So why? Because of that, we know that mu is equal to GM into rd. Hence, it is replaced with the amplification factor. And then, so already we observed that VGS parameter. So what we observed the VGS parameter? From the input loop, we observed this VGS is equal to Vi minus ID into Rs. Now I'm going to substitute this VGS further simplification or to determine the output voltage gain in terms of output voltage and input voltage. Hence, I'm going to substitute this VGS value. That VGS is equal to Vi minus ID times of Rs. Hence, so what is this? This is ID into RD. This is ID into small rd minus mu. VGS is replaced with Vi minus ID into Rs plus ID into Rs, that is equal to 0. Just you can multiply with this mu and simplify this one. So after this, we'll got this like this ID value. So ID is equal to, after the simplification, we observe this ID is equal to mu times of Vi by capital RD plus small rd plus 1 plus mu times of Rs. Now we are going to find out the output voltage. So from the circuit, we know that V0 is equal to either IL into RD, or we can also write this V0 is equal to minus ID into RD. So we got this ID value. What is ID value? That ID is represented as mu times of Vi by capital RD plus small rd plus 1 plus mu times of Rs. Hence, So now I'm going to substitute this V naught parameter. So in that the ID value is I'm going to substitute. So hence, so V naught is equal to minus mu times of Vi by small rd plus, sorry, capital RD plus small rd plus 1 plus mu times of Rs into capital RD. Now this is V naught. Now from by using this relation, now you can find out the voltage gain of the common source JFET amplifier by using the source resistance. So then we know that the voltage gain is defined as it is the ratio of output voltage to the input voltage. So what is the V naught? Minus mu times of Vi into capital RD by capital RD plus small rd plus 1 plus mu times of Rs by this is Vi. So Vi is a get cancelled, then it becomes minus mu into Rd by capital RD plus small rd plus 1 plus mu times of Rs. And this is the voltage gain for this common source JFET amplifier by considering the source resistance. And we also observe that for without source resistance, the voltage gain is represented as minus mu times of capital RD by capital RD plus small rd when the source resistance is 0, means without source resistance. So if you want to remove the source resistance, means when take the Rs is a 0, then this term is eliminated. But what happens when you are adding this source resistance to the a common source JFET amplifier? Means while adding this one, it reduces the voltage gain. So it reduces the voltage gain. Now I'm going to find out the input resistance. So according to that input resistance, then we know that the input resistance is defined as it is the ratio of input voltage to the input current. And again, from this, the input voltage is Vi is represented as VGS, and the input current is represented as IG. And from this, again, we know that, so otherwise you can write Vi is equal to VGS plus Vs. So you can write VGS plus Vs. Why? Because of the, from this, if you consider the source resistance, if you not consider the source resistance, the input voltage is represented as only VGS. When Vi is equal to VGS, if source resistance is a 0, if Vi is equal to VGS plus Vs when the source resistance is occurred. So when we are considering the source resistance is present on the source, common source JFET amplifier. But whatever it may be, when according to the FET construction, we know that the gate is a biased with a reverse voltage, hence the gate current is a very, very small, hence that is the reason we are going to assume the gate current is represented as 0. If IC is a 0, that input impedance is becomes to the infinite. Means while adding the source resistance, it does not affect the input impedance parameter. But whatever it may be, to drive the amplifier, we need to offer very large input impedance for this FET configuration. And now similarly, we need to find out the output impedance. So again, from that, the output impedance is defined as it is a ratio of output voltage to the output current while considering the input voltage is 0. So at this point, so what happens here, this RD becomes to your infinite. So for this case, let us consider from the input circuit, means this is from this case. So if you write the KVL loop equation, Vi is represented as, so one voltage source is the VGS, and here this is the RS, and another voltage source is Vs, hence Vi is equal to VGS plus Vs. Now we are taking this input voltage is 0. While determining this output impedance, we need to consider the input voltage is a 0, means Vi is a 0, that becomes VGS, and we know that Vs is equal to Is into Rs, or Is is also replaced with Id, hence Id into Rs. So from this, so you can substitute the Vi is a 0, VGS plus Id into Rs. From this, VGS is equal to minus Id into Rs. Similarly, for the output side, so now I'm going to find out, and this is Rs. So output side means I2 current is a flows across the small RD. What is I2 current? I2, we know that ID minus GM into VGS, hence. So this is I2 current. So this I2 current I represented as ID minus GM into VGS times of small RD plus, and the voltage drop across this RS, capital RS, is represented as ID into RS. We know that this is ID into RS, that is equal to V naught. Now, can expand this term, ID into RD, this is ID into RD minus GM into RS. We know that one more relation, GM into small rd is equal to mu. Hence, directly I substituted this, GM into RD is nothing but a mu times of VGS plus ID times of RS, that is equal to 0. So we observed that VGS parameter. So just now we observed this VGS is equal to minus ID into RS. Hence, now I'm going to substitute that VGS is equal to minus ID into RS in this relation to simplify this output parameter. So hence, from that I determine this V naught is equal to ID times of RD plus 1 plus mu times of RS. Now I'm going to substitute in a output impedance. What is output impedance? R naught is defined as, it is the ratio of output voltage to the output current, or is also represented as V naught by your ID. So now I'm going to substitute this V naught parameter. So what is the V naught parameter? We observed that V naught is equal to ID into small rd plus 1 plus mu times of RS by ID. So hence this ID is a get cancel. R naught becomes small rd plus 1 plus mu times of RS. But if you're not in the first case, we are not considered the source resistance. In that case, R naught is approximately equal to small rd. But while adding this source resistance across the source terminal, it is also affects the output impedance, that is 1 plus mu times of RS parameter is affects on the output impedance parameter, that is R naught is equal to, that is the reason small rd plus 1 plus mu times of RS when we consider the source resistance. So up to this point, today we observed that the analysis of common source JFET amplifier without source resistance as well as with source resistances. In that, we determine the voltage gain and input impedances as well as the output impedance. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.